Chapter 3. Method of Analysis. No great work is ever done in a hurry. To develop a great scientific discovery, to print a great picture, to write an immortal poem, to become a minister or a famous general, to do anything great requires time, patience, and perseverance. These things are done by degrees, little by little. W. J. Wilmot Buxton. Enhancing your career. Career in electronics. One area of application for electric circuit analysis is electronics. The term electronics was originally used to distinguish circuits of very low current levels. This distinction no longer holds, as power semiconductor devices operate at high levels of current. Today, electronics is regarded as the science of motion of charges in a gas, vacuum, or semiconductor. Motion electronics involves transistors and transistor circuits. The earlier electronic circuits were assembled from components. Many electronic circuits are now produced as integrated circuits, fabricated in a semiconductor substrate or chip. Electronic circuits find applications in many areas such as automation, broadcasting, computers, and instrumentation. The range of devices that use electronic circuits is enormous and limited only by our imagination. Radio, television, computers, and stereo systems are but a few. An electrical engineer usually performs diverse functions and is likely to use, design, or construct systems that incorporate some form of electronic circuits. Therefore, an understanding of the operation and analysis of electronics is essential to the electrical engineer. Electronics has become a specialty distinct from other disciplines within electrical engineering. Because the field of electronics is ever advancing, an electronics engineer must update his or her knowledge from time to time. The best way to do this is by being a member of a professional organization such as the Institute of Electrical and Electronics Engineers, IEEE. With a membership of over 300,000, the IEEE is the largest professional organization in the world. Members benefit immensely from the numerous magazines, journals, transactions, and conference symposium proceedings published yearly by the IEEE. You should consider becoming an IEEE member. 3.1. Introduction. Having understood the fundamental laws of circuit theory, Ohm's law and Kirchhoff's laws, we are now prepared to apply these laws to develop two powerful techniques for circuit analysis: nodal analysis, which is based on a systematic application of Kirchhoff's current law, KCL, and mesh analysis, which is based on a systematic application of Kirchhoff's voltage law, KVL. The two techniques are so important that this chapter should be regarded as the most important in the book. Students are therefore encouraged to pay careful attention. With the two techniques to be developed in this chapter, we can analyze any linear circuit by obtaining a set of simultaneous equations that are then solved to obtain the required values of current or voltage. One method of solving simultaneous equations involves Cramer's rule, which allows us to calculate circuit variables as a quotient of determinants. The examples in this chapter will illustrate this method. Appendix A also briefly summarizes the essentials the reader needs to know for applying Cramer's rule. Another method of solving simultaneous equations is to use MATLAB, a computer software discussed in Appendix E. Also in this chapter, we introduce the use of PSpice for Windows, a circuit simulation computer software program that we will use throughout the text. Finally, we apply the techniques learned in this chapter to analyze transistor circuits. 3.2. Nodal analysis. Nodal analysis provides a general procedure for analyzing circuits using node voltages as the circuit variables. Choosing node voltages instead of element voltages as the circuit variables is convenient and reduces the number of equations one must solve simultaneously. To simplify matters, we shall assume in this section that circuits do not contain voltage sources. Circuits that contain voltage sources will be analyzed in the next section. In nodal analysis, we are interested in finding the node voltages. Given a circuit with n nodes without voltage sources, the nodal analysis of the circuit involves taking the following steps. Steps to determine node voltages. 1. Select a node as the reference node. Assign voltages V1, V2 to V sub n-1 to the remaining n-1 nodes. The voltages are referenced with respect to the reference node. 2. Apply KCL to each of the n-1 non-reference nodes. Use Ohm's law to express the branch currents in terms of node voltages. 3. Solve the resulting simultaneous equations to obtain the unknown node voltages. We shall now explain and apply these 3 steps. The first step in nodal analysis is selecting a node as the reference or datum node. The reference node is commonly called the ground since it is assumed to have 0 potential. A reference node is indicated by any of the 3 symbols in Figure 3.1. The type of ground in Figure 3.1c is called a chassis ground and is used in devices where the case, enclosure, or chassis acts as a reference point for all circuits. When the potential of the earth is used as a reference, we use the earth ground in Figure 3.1a or b. We shall always use the symbol in Figure 3.1b. Once we have selected a reference node, we assign voltage designations to non-reference nodes. Consider, for example, the circuit in Figure 3.2a. Node 0 is the reference node, V equals 0, while nodes 1 and 2 are assigned voltages V1 and V2 respectively. Keep in mind that the node voltages are defined with respect to the reference node. As illustrated in Figure 3.2a, each node voltage is the voltage rise from the reference node to the corresponding non-reference node, or simply the voltage of that node with respect to the reference node. As the second step, we apply KCL to each non-reference node in the circuit. To avoid putting too much information on the same circuit, the circuit in Figure 3.2a is redrawn in Figure 3.2b, where we now add I1, I2, and I3, as the currents through resistors R1, R2, and R3, respectively. At node 1, applying KCL gives capital I1 equals capital I2 plus lowercase I1 plus lowercase I2. Equation 3.1. At node 2, capital I2 plus lowercase I2 equals lowercase I3. Equation 3.2. We now apply Ohm's law to express the unknown currents I1, I2, and I3 in terms of the node voltages. The key idea to bear in mind is that since resistance is a passive element, by the passive sign convention, current must always flow from a higher potential to a lower potential. Current flows from a higher potential to a lower potential in a resistor. We can express this principle as I equals V higher minus V lower all over R. Equation 3.3. Note that this principle is in agreement with the way we defined the resistance in Chapter 2. See Figure 2.1. With this in mind, we obtain from Figure 3.2 equations for Equation 3.4. Substituting Equation 3.4 in Equations 3.1 and 3.2 results respectively in Equation 3.5 and Equation 3.6. In terms of the conductances, Equations 3.5 and 3.6 become Equation 3.7 and 3.8. The third step in nodal analysis is to solve for the node voltages. If we apply KCL to n-1 non-reference nodes, we obtain n-1 simultaneous equations such as Equations 3.5 and 3.6 or 3.7 and 3.8. For the circuit of Figure 3.2, we solve Equations 3.5 and 3.6 or 3.7 and 3.8 to obtain the node voltages V1 and V2 using any standard method such as the substitution method, the elimination method, Cramer's rule, or matrix inversion. To use either of the last 2 methods, one must cast the simultaneous equations in matrix form. For example, Equations 3.7 and 3.8 can be cast into matrix form as Equation 3.9, which can be solved to get V1 and V2. Equation 3.9 will be generalized in Section 3.6. The simultaneous equations may also be solved using calculators or with software packages such as MATLAB, MathCAD, Maple, and Quattro Pro. Take this time to review example 3.1. Take this time to review example 3.2. 3.3. Nodal analysis with voltage sources. We now consider how voltage sources affect nodal analysis. We use the circuit in figure 3.7 for illustration. Consider the following two possibilities. Case 1. If a voltage source is connected between the reference node and a non-reference node, we simply set the voltage at the non-reference node equal to the voltage at the voltage source. In figure 3.7, for example, V1 equals 10 volts, equation 3.10. Thus, our analysis is somewhat simplified by this knowledge of the voltage at this node. Case 2. If the voltage source, dependent or independent, is connected between two non-reference nodes, the two non-reference nodes form a generalized node or supernode. We apply both KCL and KVL to determine the node voltages. A supernode is formed by enclosing a dependent or independent voltage source connected between two non-reference nodes and any elements connected in parallel with it. In figure 3.7, nodes 2 and 3 form a supernode. We could have more than two nodes forming a single supernode. For example, see the circuit in figure 3.14. We analyze a circuit with supernodes using the same three steps mentioned in the previous section, except that the supernodes are treated differently. Why? Because an essential component of nodal analysis is applying KCL, which requires knowing the current through each element. There is no way of knowing the current through the voltage source in advance. However, KCL must be satisfied at a supernode like any other node. Hence, at the supernode in figure 3.7, I1 plus I4 equals I2 plus I3, equation 3.11a, or 3.11b. To apply Kirchhoff's voltage law to the supernode in figure 3.7, we redraw the circuit as shown in figure 3.8. Going around the loop in clockwise direction gives negative V2 plus 5 plus V3 equals 0, equation 3.12. From equations 3.10, 3.11b, and 3.12, we obtain the node voltages. Note the following properties of a supernode. 1. The voltage source inside the supernode provides a constraint equation needed to solve for the node voltages. 2. A supernode has no voltage of its own. 3. A supernode requires the application of both KCL and KVL. Take this time to review example 3.3. Take some time to try practice problem 3.3. Take this time to review example problem 3.4. 3.4. Mesh analysis. Mesh analysis provides another general procedure for analyzing circuits using mesh currents as the circuit variables. Using mesh currents instead of element currents as circuit variables is convenient and reduces the number of equations that must be solved simultaneously. Recall that a loop is a closed path with no node passed more than once. A mesh is a loop that does not contain any other loop within it. Nodal analysis applies KCL to find unknown voltages in a given circuit, while mesh analysis applies KVL to find unknown currents. Mesh analysis is not quite as general as nodal analysis because it is only applicable to a circuit that is planar. A planar circuit is one that can be drawn in a plane with no branches crossing one another. Otherwise, it is nonplanar. A circuit may have crossing branches and still be planar if it can be drawn such that it has no crossing branches. For example, the figure drawn in figure 3.15a has two crossing branches, but it can be redrawn as in figure 3.15b. Hence, the circuit in figure 3.15a is planar. However, the circuit in figure 3.16 is nonplanar, because there is no way to redraw it and avoid the branches crossing. Nonplanar circuits can be handled using nodal analysis, but they will not be considered in this text. To understand mesh analysis, we should first explain more about what we mean by a mesh. A mesh is a loop which does not contain any other loops within it. In Figure 3.17, for example, paths ABEFA and BCDEB are meshes, but path ABCDEFA is not a mesh. The current through a mesh is known as a mesh current. In mesh analysis, we are interested in applying KVL to find the mesh currents in a given circuit. In this section, we will apply mesh analysis to planar circuits that do not contain current sources. In the next section, we will consider circuits with current sources. In the mesh analysis of a circuit with n meshes, we take the following 3 steps. Steps to determine mesh currents. 1. Assign mesh currents I1, I2 to IN to the n meshes. 2. Apply KVL to each of the n meshes. Use Ohm's law to express the voltages in terms of the mesh currents. 3. Solve resulting n simultaneous equations to get the mesh currents. To illustrate the steps, consider the circuit in Figure 3.17. The first step requires that mesh currents I1 and I2 are assigned to meshes 1 and 2. Although a mesh current may be assigned to each mesh in an arbitrary direction, it is conventional to assume that each mesh current flows clockwise. As the second step, we apply KVL to each mesh. Applying KVL to mesh 1, we obtain negative V1 plus R1I1 plus R3 times I1 minus I2 equals 0. Equation 3.13. For mesh 2, applying KVL gives R2I2 plus V2 plus R3 times I2 minus I1 equals 0. Note, in equation 3.13, the coefficient of I1 is the sum of the resistances in the first mesh, while the coefficient of I2 is the negative of the resistance common to meshes 1 and 2. Now observe that the same is true in equation 3.14. This can serve as a shortcut way of writing the mesh equations. We will exploit this idea in section 3.6. The third step is to solve for the mesh currents. Putting equations 3.13 and 3.14 in matrix forms yields equation 3.15, which can be solved to obtain the mesh currents I1 and I2. We are at liberty to choose any technique for solving the simultaneous equations. According to equation 2.12, if a circuit has n nodes, b branches, and L independent loops or meshes, then L equals b minus n plus 1. Hence, L independent simultaneous equations are required to solve the circuit using mesh analysis. Notice that the branch currents are different from the mesh currents unless the mesh is isolated. To distinguish between the two types of currents, we use I for a mesh current and capital I for a branch current. The current elements capital I1, capital I2, and capital I3 are algebraic sums of the mesh currents. It is evident from Figure 3.17 that capital I1 equals lowercase I1, equation 3.16. Take a moment to review example 3.5. Take some time to try practice problem 3.5. Take a moment to review example 3.6. Take some time to try practice problem 3.6. 3.5. Mesh analysis with current sources. Applying mesh analysis to circuits containing current sources, dependent or independent, may appear complicated, but it is actually much easier than what we encountered in the previous section because the presence of the current sources reduces the number of equations. Consider the following two possible cases. Case 1. When a current source exists only in one mesh, consider the circuit in Figure 3.22, for example. We set I2 equal negative 5 amps and write a mesh equation for the other mesh in the usual way, that is, negative 10 plus 4I1 plus 6I1 minus I2 equals 0, which results in I1 equals negative 2 amps. equation 3.1. Case 2. When a current source exists between two meshes, consider the circuit in figure 3.23a, for example. We create a supermesh by excluding the current source and any elements connected in series with it, as shown in figure 3.23b. Thus, a supermesh results when two meshes have a dependent or independent current source in common. As shown in figure 3.23b, we create a supermesh as the periphery of the two meshes and treat it differently. If a circuit has two or more supermeshes that intersect, they should be combined to form a larger supermesh. Why treat the supermesh differently? Because mesh analysis applies KVL, which requires that we know the voltage across each branch, and we do not know the voltage across the current source in advance. However, a supermesh must satisfy KVL like any other mesh. Therefore, applying KVL to the supermesh in figure 3.23b gives negative 20 plus 6I1 plus 10I2 plus 4I2 equals 0. Equation 3.18. We apply KCL to a node in the branch where the two meshes intersect. Applying KCL to node 0 in figure 3.23a gives I2 equals I1 plus 6, equation 3.19. Solving equations 3.18 and 3.19, we get I1 equals negative 3.2 amps. I2 equals 2.8 amps, equation 3.20. Note the following properties of a supermesh. 1. The current source in the supermesh provides the constraint equation necessary to solve for the mesh currents. 2. A supermesh has no current of its own. 3. A supermesh requires the application of both KVL and KCL. Take a moment to go over example 3.7. Take some time to try practice problem 3.7. 3.6. Nodal and mesh analyses by inspection. This section presents a generalized procedure for nodal or mesh analysis. It is a shortcut approach based on mere inspection of a circuit. When all sources in a circuit are independent current sources, we do not need to apply KCL to each node to obtain the node voltage equations as we did in section 3.2. We can obtain the equations by mere inspection of the circuit. As an example, let us re-examine the circuit in figure 3.2, shown again in figure 3.26a for convenience. The circuit has two non-reference nodes, and the node equations were derived in section 3.2 as equation 3.21. Observe that each of the diagonal terms is the sum of the conductances connected directly to node 1 or 2, while the off-diagonal terms are the negatives of the conductances connected between the nodes. Also, each term on the right-hand side of equation 3.21 is the algebraic sum of the currents entering the node. In general, if a circuit with independent current sources has n non-reference nodes, the node voltage equations can be written in terms of the conductances as equation 3.22, or simply capital GV, capital G, lowercase v equals I. Equation 3.23. Where G sub kk equals sum of the conductances connected to node K. G sub kj equals G sub jk equals negative of the sum of the conductances directly connecting nodes K and J, where K is not equal to J. V sub k equals unknown voltage at node K. I sub k equals sum of all independent current sources directly connected to node K, with currents entering the node treated as positive. G is called the conductance matrix, V is the output vector, and I is the input vector. Equation 3.22 can be solved to obtain the unknown node voltages. Keep in mind that this is valid for circuits with only independent current sources and linear resistors. Similarly, we can obtain mesh current equations by inspection when a linear resistive current has only independent voltage sources. Consider the circuit in figure 3.17, shown again in figure 3.26b for convenience. The circuit has two non-reference nodes, and the node equations were derived in section 3.4 as equation 3.24. We notice that each of the diagonal terms is the sum of the resistances in the related mesh, while each of the off-diagonal terms is the negative of the resistance common to meshes 1 and 2. Each term on the right-hand side of equation 3.24 is the algebraic sum taken clockwise of all independent voltage sources in the related mesh. In general, if the circuit has n meshes, the mesh current equations can be represented in terms of the resistances as equation 3.25, or simply Ri equals V, equation 3.26, where R sub kk equals sum of the resistances in mesh K. R sub kj equals R sub jk equals negative of the sum of the resistances in common with meshes K and J, where K is not equal to J. I sub k equals unknown mesh current for mesh K in the clockwise direction. V sub k equals sum taken clockwise of all independent voltage sources in mesh K with voltage rise treated as positive. R is called the resistance matrix, I is the output vector, and V is the input vector. We can solve equation 3.25 to obtain the unknown mesh currents. Take a moment to review example 3.8. Take some time to try practice problem 3.9. 3.7. Nodal versus mesh analysis. Both nodal and mesh analysis provide a systematic way of analyzing a complex network. Someone may ask, given a network to be analyzed, how do we know which method is better or more efficient? The choice of the better method is dictated by two factors. The first factor is the nature of the particular network. Networks that contain many series-connected elements, voltage sources, or supermeshes are more suitable for mesh analysis, whereas networks with parallel connected elements, current sources, or supernodes are more suitable for nodal analysis. Also, a circuit with fewer nodes than meshes is better analyzed using nodal analysis, while a circuit with fewer meshes than nodes is better analyzed using mesh analysis. The key is to select the method that results in the smaller number of equations. The second factor is the information required. If node voltages are required, it may be expedient to apply nodal analysis. If branch or mesh currents are required, it may be better to use mesh analysis. It is helpful to be familiar with both methods of analysis for at least two reasons. First, one method can be used to check the results from the other method if possible. Second, since each method has its limitations, only one method may be suitable for a particular problem. For example, mesh analysis is the only method to use in analyzing transistor circuits, as we shall see in section 3.9. But mesh analysis cannot easily be used to solve an op-amp circuit, as we shall see in chapter 5, because there is no direct way to obtain the voltage across the op-amp itself. For non-planar networks, nodal analysis is the only option, because mesh analysis only applies to planar networks. Also, nodal analysis is more amenable to solution by computer, as it is easy to program. This allows one to analyze complicated circuits that defy hand calculation. A computer software package based on nodal analysis is introduced next. 3.8. Circuit analysis with PSpice. PSpice is a computer software circuit analysis program that we will gradually learn to use throughout the course of this text. This section illustrates how to use PSpice for Windows to analyze the DC currents we have studied so far. The reader is expected to review sections D.1 through D.3 of Appendix D before proceeding in this section. It should be noted that PSpice is only helpful in determining branch voltages and currents when the numerical values of all circuit components are known. Take some time to practice problem 3.10. Take a moment to go over example 3.11. Take some time to try practice problem 3.11. 3.9 Applications DC transistor circuits. Most of us deal with electronic products on a routine basis and have some experience with personal computers. A basic component for the integrated circuits found in these electronics and computers is the active three-terminal device known as the transistor. Understanding the transistor is essential before an engineer can start an electronic circuit design. Figure 3.37 depicts various kinds of transistors commercially available. There are two basic types of transistors: bipolar junction transistors, BJTs, and field effect transistors, FETs. Here, we consider only the BJTs, which were the first of the two and are still used today. Our objective is to present enough detail about the BJT to enable us to apply the techniques developed in this chapter to analyze DC transistor circuits. Historical: William Shockley, 1910 to 1989, John Bardeen, 1908 to 1991, and Walter Brattain, 1902 to 1987, co-invented the transistor. Nothing has had a greater impact on the transition from the industrial age to the age of the engineer than the transistor. I am sure that Dr. Shockley, Dr. Bardeen, and Dr. Brattain had no idea they would have this incredible effect on our history. While working at Bell Laboratories, they successfully demonstrated the point contact transistor invented by Bardeen and Brattain in 1947, and the junction transistor which Shockley conceived in 1948 and successfully produced in 1951. It is interesting to note that the idea of the field effect transistor, the most commonly used one today, was first conceived in 1925 through 1928 by J.E. Lilienfeld, a German immigrant to the United States. This is evident from his patents of what appears to be a field effect transistor. Unfortunately, the technology to realize this device had to wait until 1954 when Shockley's field effect transistor became a reality. Just think what today would be like if we had this transistor 30 years earlier. For their contributions to the creation of the transistor, Dr. Shockley, Dr. Bardeen, and Dr. Brattain received in 1956 the Nobel Prize in Physics. It should be noted that Dr. Bardeen is the only individual to win 2 Nobel Prizes in physics. The second came later for work in superconductivity at the University of Illinois. There are 2 types of BJTs, NPN and PNP, with their circuit symbols as shown in Figure 3.38. Each type has 3 terminals, designated as emitter E, base B, and collector C. For the NPN transistor, the currents and voltages of the transistor are specified as Figure 3.39. Applying KCL to Figure 3.39 gives I sub E equals I sub B plus I sub C, where I sub E, I sub C, and I sub B are emitter, collector, and base currents, respectively. Similarly, applying KVL to Figure 3.39b gives V sub CE plus V sub EB plus V sub BC equals 0, equation 3.28, where V sub CE, V sub EB, and V sub BC are collector emitter, emitter base, and base collector voltages. The BJT can operate in one of 3 nodes: active, cutoff, and saturation. When transistors operate in the active mode, typically V sub BE, approximately 0.7 volts, I sub C equals alpha times I sub E, equation 3.29, where alpha is called the common base current gain. In equation 3.29, alpha denotes the fraction of electrons injected by the emitter that are collected by the collector. Also, I sub C equals beta I sub B, equation 3.30, where beta is known as the common emitter current gain. The alpha and beta are characteristic properties of a given transistor and assume constant value for that transistor. Typically, alpha values in the range of 0.98 to 0.999, while beta takes values in the range of 50 to 1000. From equations 3.27 to 3.30, it is evident that I sub E equals parentheses 1 plus beta end parentheses times I sub B, equation 3.31, and beta equals alpha over 1 minus alpha, equation 3.32. These equations show that in the active mode, the BJT can be modeled as a dependent current-controlled current source. Thus, in circuit analysis, the DC equivalent model in figure 3.40b may be used to replace the NPN transistor in figure 3.40a. Since beta in equation 3.32 is large, a small base current controls large currents in the output circuit. Consequently, the bipolar transistor can serve as an amplifier, producing both current gain and voltage gain. Such amplifiers can be used to furnish a considerable amount of power to transducers such as loudspeakers or control motors. It should be observed in the following examples that one cannot directly analyze transistor circuits using nodal analysis because of the potential difference between the terminals of the transistor. Only when the transistor is replaced by its equivalent model can we apply nodal analysis. Take a moment to go over example 3.12. Take some time to try practice problem 3.12. Take a moment to go over example 3.13. Take some time to try practice problem 3.13. 3.10. Summary. 1. Nodal analysis is the application of Kirchhoff's current law at the non-reference nodes. It is applicable to both planar and non-planar circuits. We express the result in terms of the node voltages. Solving the simultaneous equation yields the node voltages. 2. A supernode consists of two non-reference nodes connected by a dependent or independent voltage source. 3. Mesh analysis is the application of Kirchhoff's voltage law around meshes in a planar circuit. We express the result in terms of mesh currents. Solving the simultaneous equation yields the mesh currents. 4. A supermesh consists of two meshes that have a dependent or independent current source in common. 5. Nodal analysis is normally used when a circuit has fewer node equations than mesh equations. Mesh analysis is normally used when a current has fewer mesh equations than node equations. 6. Circuit analysis can be carried out using PSpice. 7. DC transistor circuits can be analyzed using techniques covered in this chapter. This concludes the reading of Chapter 3. Thank you for listening. I hope it helps your understanding of the material.